Hello there, Mr. Sutton here, bringing you the AB Calculus 610 Extra Practice Number 1 solutions on rate in, rate out. For this problem, we have a tank with 125 gallons of heating oil at time 0, and during the interval from 0 to 12 hours, heating oil is pumped into the tank at a rate described by this h of t function, and it's removed from the tank at this r of t function's rate, and both of these are gallons per hour. So before I go further, I'm just going to take a minute to enter these in my y equals in my calculator because I'm pretty sure I'm going to have to use them. So here we go. I've entered my h of t function as y1 and r of t is entered as y2. Great. Now moving on to the first part of this problem. How many gallons of heating oil are pumped into the tank during the interval 0 to 12? Well, I have this function that gives me the rate at which gallons are pumped in, so I just need to integrate this rate to get the total amount of heating oil pumped in. So I'm doing the integral of h of t from 0 to 12. And now I'll just use the calculator for this. So here's what I'm putting on my calculator. Remember that I stored h of t as y1, so I'm just doing 0 to 12 integral of that. And that is going to give me, let's see here, 70.571, and that's going to be gallons of heating oil. For part B of this problem, we want to know if the level of heating oil in the tank is rising or falling at time 6. So to make my life easier on this and the rest of the problem, I'm going to just define a new function, L of t, as the level of heating oil. And then I can define the derivative of this, the rate of change of heating oil, as the rate in minus the rate out, h of t minus r of t. And now I can use this whenever I need to. Now would be a good time, because if I want to know if the level of heating oil is rising or falling, I need to know the value of L prime of 6. So let me go to the calculator. And on my calculator, you'll see down here I've defined a third function, y3, as y1 minus y2. So this is my L prime down here. This is h of t minus r of t. Quitting out of there now, I'm going to do alpha trace, call up y3, and then I'll just open a parentheses and plug 6 into that. And that gives me a value of negative 2.924. Now, significantly, this is negative. Since the derivative of heating oil level is negative, that means the level of heating oil is falling at time 6. For part C, we want to know how many gallons of heating oil are in the tank at time 12, and we kind of saw this coming, so that was why we defined that L of t function as the level of heating oil. So we're going to ask for L of 12 on this one. L of 12 is going to be the original amount of heating oil, which was 125, plus the total change in heating oil from 0 to 12. So that's going to be the integral of L prime of t dt from 0 to 12. And now I'm just going to plug that in my calculator. So this is where I'm really glad I've defined that y3 function for L prime. So I've got 125 plus math 9, integral from 0 to 12 of, now alpha trace y3, because that's where I defined L prime in the calculator, dx, and all that very quickly comes out to how much? Well, maybe not so quickly. 122.026. And that's going to be in gallons. For this last part of the problem, we want to know at what time is the volume of heating oil the least, and show the analysis. So in order to do this, we're going to try the candidates test. At some point, we're going to plug 0 and 12 into the L function that we defined earlier. But we also need to plug in critical values, and we also need to find them. So to find them, I'm going to let L prime of t equals 0, and I'm now going to solve that on my calculator. So I'm going to be graphing this y3 function, y1 minus y2. Again, that's where I stored L prime of t. And I'm going to go to Window, and I'm going to make that from 0 to 12, because that's the interval that they gave us in the problem. And let me do a zoom 0, zoom fit, and see what this graph looks like. And actually, before I do that, let me go back to my y equals. I'm going to deselect these other rates of change because I don't really want to see them. All right, now let's try zoom 0. See what we come up with. So here we are going from 0 to 12. This is just L prime of t now. And we see that we've got, let's see, 1, 2 zeros here. So let's go ahead and take a look at these. Now, Actually, we don't really need both of these. If we're trying to find when the volume of heating oil is the least, we're looking for the absolute min, which means we only need to find local mins in terms of critical values. Like we have this value right here where we're going from positive to negative, but that's a local max for the amount of heating oil. So there's no way that's going to be the minimum value if it's not even smaller than the values immediately around it. So we're really just going to look at this other value here where we're going from negative to positive. So I'll do second trace 0. And let me just move my spider closer to that. So let's see here. We're somewhere between 11 and 12. So I'll press enter on the other side, press enter one more time, and we have a value of about 11.3185, which I'm going to quit out of my graph and actually store as an A value, or I'll store it as alpha A, but you really could store it as any letter you wanted. So let me try this here. There we go. And that's stored now as A, so I can pull that back anytime I want. So I'm going to write here, I mean, I've drawn this, but I didn't really draw it on my work. I observed on my calculator that L prime of t is changing from negative to positive at t equals A equals that crazy value only. So here I've effectively said, hey, there may be other critical values, but they're not local mins, so I don't really care about them. So this is the only critical value I now have to consider, just the way I've worded this. I also made this A. I defined this value as A, so now I can rewrite this. Instead of rewriting this, I'll just use A the whole time. Okay, time for my candidates test. So I've got L of 0, the original amount of oil. That's 125. They gave that to us. Now for L of A, the level of oil at time A, that's going to be the 125 I started with, plus the integral from 0 to A of L prime of t dt. And I'll need the calculator to figure this out. So 125 plus math 9, integral from 0 to A, so alpha A, or whatever letter you stored it as. And now L prime we stored as alpha trace y3, and then dx. So pretty much what we did to find L of 12 on part C. And that gives us a value of 120.738. So far, that's the min. Let's see if we can do better with this last endpoint. Now, I mean, you can look at this graph and see we're not going to do better, because if we have a positive derivative, that means our oil level is increasing after this point. But it's easier just to kind of plug that in. In fact, we are actually already found the value of L of 12. If you look back on the last part of the problem, L of 12 was this 122.026 value we found in part C. So we already kind of had that one for free. We might as well just write it here so we can show them we're considering it. Now looking at all these values, 120.738 is the least, and they just wanted to know at what time is the volume the least. So we'll just tell them the time. We've already defined that time as A, so we're just going to say we have our min at A hours. For this problem, the setup here is that we have this tank with 100 liters of water at time 0, and we have this piecewise graph showing us R of t, which is the rate in liters per minute at which water is being pumped into this tank over 55 minutes. So for the first part of this problem, they just want us to find R prime of 45 and then explain what that means in the context of the problem. So let's start with the purely mathematical part. R prime of 45, that is the slope of the R function at time 45. Now, since time 45 happens on a line, if we find the slope of that line, we have figured out R prime of 45. So we can say R prime of 45 is just going to be, and now I'm setting up a slope here, 0 minus 30, so that's the y values, over 55 minus 35. That's negative 30 over 20, or negative 3/2. Now, what does that actually mean? Well, R itself is the rate at which water is being pumped into a tank. So this means that at 45 minutes, the rate at which water is being pumped into the tank is itself decreasing at a rate of 3/2. And what's the units going to be? This is going to be liters per minute, so liters per minute squared. The rate at which this is changing with respect to time is just basically these units divided by another time unit of minutes. For part B of this problem, we want to know how many liters of water have been pumped into the tank from time 0 to 55, with work. All right, well, we've got the rate at which water is being pumped in here. So to actually figure out the amount of water pumped in, we have to integrate this rate of change. Now to do that, we essentially need to find the area under the curve. So mathematically, we're taking the integral from 0 to 55 of r of t dt. And what that looks like over here, well, our first shape going from left to right, we've got a trapezoid here. So this is going to be a base of 10 plus a base of 30 divided by 2 times a height of 20. Next, we have, you could split this up into a rectangle and a triangle, or you could just make it one big trapezoid. So a normal facing trapezoid here, I've got a base of, let's see, 20 to 35 is 15. And down here, 20 to 55 is going to be 35. So we have 15 plus 35 over 2 times a height of 30. And now we could simplify this if we wanted to. This is going to be, let's see here, 20 times 20, which is 400. Over here, we've got 50 over 2, that's 25, times 30 is 750. Adding these together, that's going to be 1,150, and that's going to be liters because we're finding the area under here. So you're essentially doing liters per minute times minutes, which just cancels the minutes and leaves you with liters. All right, so that was liters, and that's it for this part of the problem. For part C, they're telling us that at time 10 minutes, so right here, water begins draining from the tank at a rate modeled by this D function that they just gave us. And then they say it continues to drain until time 55. We want to know, based off of this, how many liters of water in the tank at time 55 minutes. So this is a how much is in minus how much is out kind of situation. We're starting with 100 liters, so that should definitely be our starting point. And to that, we're going to add the 1,150 liters that have been pumped into here over the whole 55 minutes. And we found that value, you might remember, in part B. So this is how much water came in. Now let's subtract the water that's going out. This D function is the rate at which water is going out. If I want to figure out how much actually drained out, I need to integrate this thing from, they said 10 minutes to 55 minutes, because that's when this function is actually working. So I'm going to take the integral, I'm going to subtract the integral of d of t from 10 to 15. And for this, I will need the calculator. So I'll begin my calculator journey by putting this d function in my y equals under y1. And then quitting out of that, I've got 100 plus 1,150 minus, and now I'll math 9 this thing, integral from 0, no, not 0, from 10. It's usually 0, but now it's 10, from 10 to 55 of, and I'll do alpha trace y1 to pull up my d function, and we'll make that dx. All of that's going to come out to approximately, dum-da-dum, it's taking it a while. There we go, 799.725, and that is going to be liters. For this part of the problem, they want us to use the functions r and d to figure out the amount, whether the amount of water in the tank is increasing or decreasing at time 45. So r is the rate at which water is coming in, d is the rate at which it's going out, draining out. We just need to figure out which of these is larger, most positive, at time 45. So let's find r of 45 first. To do that, we're just going to have to look it up on the graph here. Now, it's a little difficult to see exactly what the y value is when the input value here is 45. So let's just go ahead and use the equation of a line. So I'm going to do y minus y1 equals m times x minus x1, point slope form. I'm going to say y minus 30 equals our slope that we found earlier of negative 3/2 times x minus 35. And using this now, I can just plug in 45 for x and figure out what y is based off of that. So I'm going to say that r of 45, y, equals the following. So I'm going to add 30 to the other side. I still have the negative 3/2. And inside here, I now have 45 minus 35 because I want to know what y is when x is 35, or 45 rather. There we go. So we've got negative 3/2 times 10. That's negative 15. 30 minus 15 is 15. Next, I need to figure out d of 45. And for that, I'm going to use the calculator. On my calculator, I've already stored the d function as y1, so now I'll just plug 45 into that, and that gives me about 10.888. So 15, in other words, r of 45, is greater than 10.888, which is to say the input is greater than the output. The rate in is greater than the rate out. That means that our water must be increasing at time 45. For this problem, we're talking about snow. There's no snow on Janet's driveway when snow begins to fall at midnight. From midnight to 9 a.m., snow accumulates at a rate modeled by this f of t function right here. And this is in cubic feet per hour. And that's hours since midnight. Now, Janet starts removing snow at 6 a.m., up bright and early. Well, probably not so bright at this time in the winter, right? But the rate that she's removing snow is given by this piecewise function here. So you can see that between 0 and 6, she has a rate of 0 because, well, she's probably sleeping. Good for her. Between 6 and 7, she's going at a brisk pace of 125 cubic feet per hour, and then she gets tired and slows down for that 7 to 9 stretch there. So we want to know how many cubic feet of snow have accumulated on the driveway by 6 a.m. What is Janet waking up to? For this, we are going to use our f of t function. We just have to integrate this thing, the rate of change of snow, at least the rate of snow accumulation, from 0 to 6. So that's what we're doing here. Integral from 0 to 6 of f of t dt. And for this, we will use the calculator. To help me out on this, I'm entering my f of t function as my y1 function in y equals. So 7x times e to the cosine of x, same thing as t. Quitting out of this now, let me do math 9. So integral from 0 to 6 of alpha trace y1 dx. That gives me f of t in there. And pressing enter now, let's see how much snow is there. That's going to be 142.275, and that's cubic feet of snow. For part B, we want to find the rate of change of the volume of snow on the driveway at 8 a.m. So this is the rate of change of the overall amount. This is going to be the rate in minus the rate out, f of t minus g of t. In particular, we're going to be doing f of 8 minus g of 8. F of 8 we're going to have to find on the calculator. G of 8 we can find right away. That follows the rule in the interval from 7 to 9 because we're plugging in 8. So that would just be 108. So then we're doing f of 8 minus 108. And to do that on the calculator, I've got y1 of 8 because that's where I stored my f function, minus 108. Comes out to negative 59.583. And this is the rate of change of snow. So this is going to be cubic feet per hour. For part C, let h of t represent the total amount of snow that Janet has removed from our driveway after t hours after midnight. We want to express this as a piecewise function with the domain 0 to 9. All right, so basically we're taking these rates of change and trying to convert them into accumulations, and we need to do it in a piecewise fashion. So let's start with our first case, time between 0 and 6. Well, in that case, we can say that h of t, the amount of snow removed, is 0. I mean, Janet's not removing snow if she's sleeping, unless she's sleep shoveling. I wish I could do that, but Janet can't. So 0 for that first interval. For the next interval, we need to take the rate of change, 125, and multiply it by the amount of time Janet's actually been going at that rate for. So if we're asking how much Janet has removed by, say, 6:30, we're not multiplying this by 6.5 because Janet has not actually been shoveling snow for 6.5 hours. We have to multiply it by whatever this time in here is minus the first 6 hours that Janet was doing nothing. So to capture this, I'm going to say for the interval from 6 to 7, h of t is 125 times t minus 6. That way we're just counting the hours after 6 a.m. Now for the last interval, this one's a little bit trickier. For 7 to 9 for the times, I need to take first the amount of snow that Janet shoveled from 6 to 7. So we're going to write that this stuff equals h of 7, which is the amount of snow Janet has removed by 7, and then to that we're going to add this other little piece. So we have 108, that's the rate, And to make sure that we don't count anything except what Janet shoveled after 7 a.m., we'll do T minus 7. So, for example, if I want to find out how much snow Janet has removed at time 8, I would do 8 minus 7, so that's just 1 hour at this rate, plus all the snow that Janet already removed up until 7 a.m. So just to write this out without this h of 7 here, I can write 125 instead of h of 7, because if Janet's been shoveling at this rate, 125 for 1 hour, she's shoveled exactly 125 cubic feet of snow. All right, putting it all back together in a piecewise function, I've got 0 for this first interval, as we discussed, 125 times t minus 6 for this middle interval, and finally, I've got 108 times t minus 7 plus 125 for this last interval. For this last problem, we want to know how many cubic feet of snow are on the driveway at 9 a.m. So the amount of snow accumulated is going to be the amount that we started with, which they said was 0. There was no snow on our driveway when it began, plus the amount of snow that accumulated here over time. So that's going to be the integral from 0 to 9 of f of t minus the amount of snow, h of 9, that Janet removed by 9 a.m. So 0 to 9 integral, we can do that on the calculator. H of 9, that's going to be the 125 she removed from hours 6 to 7, plus we had 2 hours removing at the rate of 108. So we're going to have to do 2 times 108. So putting all this on the calculator, I'm going to go math 9 and take the integral from 0 to 9 of alpha trace y1. So this was my f of t snow accumulation function. And then we'll do a dx there. Minus. So now to figure out how much snow is actually left, I have to see how much Janet removed. So she shoveled 125 cubic feet from 6 to 7. And again, she had 2 times this 108 from 7 to 9. So subtracting all of that snow from the ground, we end up with a grand total of how much? 26.335 cubic feet of snow.